Okay, it's technically 2 o'clock, so I guess I'll get started. So this is a tutorial on how to use Traceroute, and I'm sure a lot of people in this room think they know how to use Traceroute or do know how to use Traceroute properly, but the point of this is to provide an archive for people, provide a reference that people can look at, things like that. So you're troubleshooting a problem on the internet. All of us do that every day. The number one go-to tool, obviously, is Traceroute. Every OS comes with Traceroute. There's billions of websites out there that have looking glasses, that have visual Traceroute tools. All of your customers and clients have Traceroute, and anyone that's ever looked at their NOC tickets is well aware of that. And it seems really simple to use. There's, you type in an IP address and you see a list of routes in your path, and anyone that's ever looked at their NOC queues realizes that most of the world thinks that wherever the traceroute stops or wherever the latency goes up, that's where the problem is. And then they will send you email accordingly. And it turns out that reality couldn't be further from the truth. And by the way, this is, I don't know how I'm going to fill an hour and a half, so everyone feel free to ask lots of questions. So, no cookies. So, what's wrong with just looking at Traceroute and seeing where the problem is, and there you go. Well, it turns out that these days most networks are actually pretty well run. Obviously there's exceptions to the rule, but for the most part you don't see as often the situation where, oh look, it's a congested link and Traceroute shows it to me instantly on my forward path. More and more you're seeing complex issues. You're seeing problems where just looking at Traceroute and seeing where the latency goes up or where it stops is absolutely no value at all. And the reality is that very few people are actually skilled at reading Traceroute. Anyone that has ever sent in a Traceroute to another network a lot of the times knows that they just get dismissed because the people reading the Traceroutes are trained to dismiss everything because the vast majority of the complaints that come in are completely false or whatever. So there's not a lot of knowledge out there about how to correctly read and understand a traceroute. So the topics to discuss here, we talk about how traceroute works in general. We talk about how to interpret DNS in Traceroute, figure out what city the router's in, what type of router it is, what speed the interfaces are, things like that. How to understand the network latency, understand when there's a problem, when there's not a problem, what are the contributing factors. To understand asymmetric paths in Traceroute, to understand multiple paths in Traceroute, and to understand some of the effects of MPLS networks when you're tracerouting through them. And just as a random Traceroute factoid, anyone that uses the Unix version of Traceroute knows that the port starts from 33434, which turns out to be to the power of 15th plus the mark of Satan, which there might be some relationship there. I don't know. So the 10,000-foot overview of how Traceroute works, which I'm sure most people know, but the gist is you launch a probe packet towards whatever your destination IP is with a TTL of 1, and every router that touches the packet decrements the TTL by 1, and when the TTL hits 0, the router discards the packet and sends back an ICMP message that says the TTL was exceeded. So this mechanism is there to prevent routing loops, but it also helps for Traceroute because you're able to send out incremental probes and see every hop along the way. So it goes back to step 1. You send out a packet with a TTL of 2 this time, then 3, then 4. And you see all the hops along the way until the final hop in the classic Traceroute, it's UDP. So what happens is you assume that nothing's listening on that UDP port, and then the host is going to send back a destination unreachable, and that's going to indicate to Traceroute, we're done, you can stop. So it's actually a little more complex than the general overview because there's multiple probes going on. The default for most Traceroute implementations is 3 probes. That's why you see 3 latency results. And something to note there is that every probe, every time it sends a probe, the destination port is going to increment. So it's not just going to be the same path every time. Any time that you are hitting multiple paths along the way, you could, if you're hashing at layer 4, you could take a different path. And not only can that happen with ACMP, where you have two links in parallel that are running your IGP that are load balancing at layer 3, that can even happen over a 802.3AD link, where you see problems with some of your packets, and it turns out that invisibly to you, one of those packets is getting hashed over one bundle with a problem, and the other one isn't. So it's something to keep in mind. And obviously not all traceroutes use UDP. Windows famously uses ICMP, so any people that are filtering ICMP or not filtering UDP or whatever will see different results. And obviously a lot of the traceroute tools out there now give you the option to use whatever you want, and one reason to use TCP is you can get through firewalls if people are allowing that through. The probe doesn't matter. The probe is irrelevant. It's a packet that goes out that expires. So it could be TCP, it could be ICMP, it could be anything that will fit an IP, as long as it gets routed and then the TTL expires and gets dropped. So correct. You're just sending a TCP packet, the concept being to get past a firewall or whatever. So how is the traceroute latency calculated? Well, what happens is you take a timestamp of when you send out the probe packet, and then you take a timestamp of when you receive the ICMP back. And obviously you look at the difference. So the routers along the paths don't actually do any processing. So you have no idea when the router that's responded or when the destination host that's responded. They don't do anything. They don't put any time information in the packet. They don't do anything. But a lot of times what happens is the traceroute program itself encodes the launch time in the packet itself. The reason for that, number one, it reduces state, so the program doesn't have to keep track of what time it launched the packet. It gets the return packet back, and it has all the state that it needs. And the other reason is that it increases accuracy, that you can encode a higher timestamp value in there. Anyone that's ever done a traceroute off a Cisco router knows that iOS has very low granularity within 4 milliseconds. So you see 0 or 4 even if the value is 1, 2, or 3. Whereas most traceroute implementations on hosts are down to the sub-millisecond, microsecond range. But the key point here is that what you're really measuring is the round trip. You're measuring the time for the probe to get to the router that dropped it, and you're measuring the time for the ICMP packet to come back. So here's a little bit of detail about what hops you're actually seeing. A lot of people are confused by this because they don't understand whether they're seeing an ingress interface or an egress interface. But so if you look, if I had a laser pointer, I would be better. But if you look at the first packet coming out, coming from the source with a TTL of 1, and it hits router 1. Router 1 drops it, and it sends back its ICMP TTL exceed. The path that it sends it back via, you have no visibility into, and it doesn't have to match the ingress-egress interface, the egress interface. It doesn't have to match anything. So it just goes back via whatever it thinks the best route to whatever your source address was. Then you see as it goes through the second interface with a TTL of 2, it goes out the egress interface of the one router, comes into the ingress interface of the second router, and what you're seeing in Traceroute every time is the ingress interface. So in this example here, you're seeing the 172.162.1, you're seeing the 10.3.2.2, you're not seeing the return path, and you're not seeing the egress interface. You're seeing the ingress into each router. And another random factoid, Traceroute, as it actually is implemented, shouldn't work. If you actually look at RFC 1812, which has never been replaced or updated, it actually says that the ICMP source must be from the egress interface, which, if you did that, would completely change the way Traceroute works. So just one of those random factoids that the de facto standard doesn't match what's actually specified, and that's just the way people have always done it. What was the question?
Is that true on all routers?
It is true on all routers, and there's actually some cases where people have followed the standard correctly and thus been incorrect. Some notorious examples of this are Foundry Sonnet cards, which followed this implementation and started returning the wrong addresses. So you were seeing the path out instead of the path in. But
Traceroute is back. Combination of Traceroute, back, so it back results and stuff like that. So that analysis is back, and if you go back 16 routes, it's only more hot.
exactly, and I'll talk about that more later. But that's one of the key points of Traceroute is that you're really looking at the forward and the reverse path, but you're only seeing the forward path, and even then, the fact that you're seeing the forward path is an actual violation of the standard, but it just is the de facto way that things were done. So we talk about how to interpret DNS in a traceroute for any network that is not Google, because Google, for whatever reason, doesn't believe in DNS. Everyone else does. So the things that you want to pick out of DNS, you want to figure out location identifiers. You want to figure out where a router is in the world. Maybe you want to figure out where the router is, like a colo facility, if it's in a Equinix or a PAX or something completely different. You want to figure out what type of interface the packet is going over. You want to figure out what capacity is available. And in some cases, you want to know what's the router type and role. Is this a core router? Is this an edge peering router? Is this a customer aggregation router? Or whatever the case may be. And then a lot of times you want to figure out where the network boundaries are and the relationships. So you want to know when you cross between Global Crossing and Sprint, and you want to maybe figure out that that's a peer versus a transit relationship or something like that. So the reasons you want to know location, obviously, if you can identify incorrect or suboptimal routing. If you're going from Chicago to Chicago and it happens to go through Atlanta and Indianapolis, like my Comcast cable modem used to, maybe you want to identify that. It also helps you understand where the interconnections are happening. So if you're routing out to LA, the reason for that from Phoenix might be that that's where the peering point is. And it helps you understand, you need to know the location to understand when the latency is or isn't a problem. So the most commonly used location identifiers, you've got airport codes, silly codes, and just random attempts to abbreviate things based on either the English name, or a lot of times people have their own little internal codes that no one can really figure out. But you could either ask someone, or sometimes people have these on their websites, or you can just try to reverse engineer it, and sometimes you just have no idea what the hell people were thinking.
Did you find REN codes are still in use?
The REN codes are no longer in use, I don't think. I don't know. Tom Scholl would know. Famously, REN referred to everything by the SBC codes that they used, to the point that a lot of people just started calling them REN codes. So it was a handy identifier for figuring out, Equinix in Ashburn or whatever the case may be. But I think those have all been migrated now, or maybe not, I don't know. So airport codes. The reason people use airport codes is you've got really good international coverage, and you've got good coverage over most large cities. So, if there's a city that's worth mentioning, it's probably got an airport in it. And that's probably where you're putting your routers and things like that. So some examples: Santo Domingo, obviously, anyone that flew in is SDQ. San Jose, California, SJC. They're three-letter codes that are defined, standardized, and you can go Google them and find them. Sometimes the people are representing things by pseudo airport codes, which sometimes there's an actual code that covers a metro region where there's multiple airports, and sometimes people just use codes that are not the actual code, but they're close enough for people to understand. So, for example, in New York, rather than put JFK or LGA, or a lot of people might even fly into Newark, they're just going to write NYC, and people can pretty much figure out that NYC means New York. Same thing in DC, where you've got Northern Virginia covered by AD, you've got Washington DC itself covered by DCA. A lot of people are just writing WDC for the entire region. Silly codes are common language location identifiers. So the full codes themselves are maintained and sold by Telcordia, and they're mostly used by telephone companies. So you're going to see, as a telco, you're going to see a code like that identifying Houston, Texas, and it's going to identify some CO somewhere, and it's going to identify a rack and a port and a position, whatever. For the most part, internet-wise, you don't need that much detail. But there's the first 6 letters are called the geopolitical and geopolitical and geo something or another, basically city and state. And you've got really good coverage of everywhere in the U.S. certainly that has a telephone, which is better coverage than everywhere that has an airport. So you're going to see this mostly used by networks that have a lot of pops that really want to distinguish between 5 neighboring cities within a common metro area. So you might not want to just call something DC. You might really care if it's Herndon or Sterling or whatever the case may be. And the problem here is that there's not much standardization for international coverage. So you see some networks, NTT being the biggest example, that just make them up. So Amsterdam, Netherlands, they're just going to make up a code. And then, of course, you've got the arbitrary values. So, for example, if you don't know what an airport code is and you don't know that Chicago O'Hare, which was originally named after Orchard Field, or Midway, you may not know that ORD has anything to do with Chicago. So you may find a lot of people just putting CHI. And there's a lot of arbitrary codes where it's close enough to something that people would recognize. Toronto's another example, YYZ, who would know that that's Toronto unless you happen to know that that's an airport code. So people just write TOR. And obviously there's some benefits there. If you're looking at the traceroute, you can kind of figure out what that might be, even if you don't know the airport code. The downside being it's not a standard, so you can't go Google it and know for sure. So I did a list of common airport codes and SILI codes for the major locations in the U.S., and the hope being that people can look at this document later and parse some of their own trace routes and figure things out. And in some cases there's some cities that are notorious for having other codes associated with them that are not the airport codes. So there's the major U.S. locations and then the major non-U.S. locations. And obviously the star on the SILI codes is I just stole whatever NTT uses since they seem to be the primary users of SILI codes that are not in the U.S. So the next thing that you might care to interpret is interface type. Most networks are making a good faith effort to put it in DNS, not only to help random Joe user on the internet, but to help themselves, because sometimes they have to trace route through their own network and figure out what router and what interface it's on, and it's very helpful to have that information. So there's a lot of networks that are actually doing this automatically. I do it automatically via SNMP. It's not terribly difficult to do. So most of the big networks are doing that. And you can use that information to figure out not only the interface type, but even the maker model of the router. For example, this is one of my interfaces to level 3. You can look at the interface name and see XE- something, it's a Juniper 10 gig port. The card starts at 11, so you know that the router has at least 12 slots, and it's a 10 gig port, and it's in a not zero numbered PIC slot, so you know that it's a 40 gig card, so you know that it's a Juniper MX960. No other device could fit that profile. Handy to know. And I have a list of common interface names that you might see. So a lot of people put the short name, which is actually will pull directly off of SNMP. So you'll see these type of names out there most of the time for the different interface types, or for Ethernet bundles or SONET bundles. And they're different depending on if it's iOS or XR or Juniper. Some people do. Some people do obfuscate. Well, obviously, the number one thing that people do, like Google, just doesn't put DNS, or maybe they have a name server that they use internally that returns the correct results, but globally outside the network it doesn't. There are some cases where people have picked a standard. Level 3 used to do this at some point, and there's a couple other people that do too, where even if it's not a Juniper or even if it's not a Cisco, they name it after the opposite style. And in that case, you just don't know what kind of router it is. But there's people that lie, obviously, that claim they have a 10 gig when it's really a fast E or something. But you're going on what people are telling you. So Then you want to interpret DNS and figure out the role of the router. The hard part here is that every company and every network uses their own standards, and there's no real standards. But there's a lot of common patterns that you can find. So I just listed some of the most common names that people are using. Core routers, gigabit core routers, terabit core routers, Ethernet backbone routers, core, whatever you choose to call it. It's some device that is interconnecting the rest of your network to itself. There's your dedicated peering routers, and a lot of people are combining core and peering routers, so it's harder to tell, but some of the common names are border routers, border edge, interconnection routers, internet gateway, peer, whatever you choose to call it. And then more commonly, you see dedicated routers for customer attach. Some people call them access routers, aggregation devices, customer access, high-speed access, or just gateway. So when you see those routers, you know, especially if it's a company that follows a certain standard, you know, you see a GW and you know that it's a customer, and that can be helpful for figuring out what the paths are and who's doing what. And then the other thing you want to identify is the network boundaries. The reason for that is when you cross network boundaries, that's where you start to see asymmetric paths happening. Because as soon as I cross a border from Global Crossing to Sprint, Sprint is now using their own local prefs and their own values to determine how that path's going to get back to me, and it's very likely to be completely different than it was before you crossed the network boundary. So you want to be able to identify that. And even more importantly, you want to be able to identify the customer edge, because that's a common source of incorrect traceroute analysis, is where people see the traceroute stop on certain things and they say, well, here's the example of it working correctly, here's the example of it not working correctly, and it stops right here and it has your name in it. Well, it might have your name in it, but it might be your network customer premise or whatever. It's the customer router, but it's your /30. So they associate it with you, so they open the ticket with you, even though it's actually the customer side. So you want to be able to identify where that demarcation point is. And there's a lot of networks that will do nice things, like actually put customer or otherwise make it very clear what the demarcation point is. So here's some examples of doing that. You know, obviously it's really easy to see when you've now crossed from Global Crossing to Sprint, but that only happens when both sides are setting the DNS correctly. So what tends to happen is you have, you know, a /30 or whatever block interconnecting two networks, and that IP address tends to be owned by one of the parties. So the only way that the DNS is set correctly for the opposite side is if they talk to the other side and say, what DNS do you want, and then they go set it. And that tends to not happen in a lot of cases. So you see, for example, here's a Cogent peer where what they do is they name it, you know, it's named after the Global Crossing side of the interface, but that's actually the Cogent side. It just happens to be Global Crossing's block, and Cogent didn't supply them information, so they name it Cogent dash whatever. And what you can do, remember when I was showing that the traceroute is always showing you the ingress interface, what you can do is look for the other side of the /30 and see what's the egress interface. So for example here, you go look at .89 instead of .90, and you know you can do math on CIDR blocks and figure out what the other side of the /30 is, and there's the actual information. That's the egress interface on Global Crossing's router, and you know that the other side is Cogent. So that's how you can get some of that information. So understanding network latency is a big problem with Traceroute. So basically there's three types of delay or network latency that you have to concern yourself with. The first is serialization delay, which is caused by having to transmit packets in one complete entity. You can't start the next packet until the first packet finishes. So the time that you're transmitting that packet is a serialization delay. You have to wait for the whole thing to come through. There's a queuing delay, which is time spent in the router queues waiting for transmission, which is mostly associated with just the interfaces being full. And you've got propagation delay, which is how long it takes to actually transmit the message over whatever the medium is, fiber, or whatever the case may be. And that's primarily speed of light based or whatever. So serialization delay, there's a little more detail on it, but basically what I said before. It's not much of an issue in modern networks, and the reason for that is over time, interfaces have gotten many orders of magnitude faster, while packet sizes have stayed about the same. So these days you find most router links 100, 1,000 times faster than they used to be when it was a 56K line, but the packet sizes are not 100 or 1,000 times bigger. They're mostly the same. So these days, this is very little of a problem. But if you're talking about very slow networks, very small networks, whatever the case may be, every time you have a router hop that has to interact with a packet on the packet level, you're introducing this delay because you can't continue transmitting the beginning of the packet until the whole thing is received. So if you've got a network built of T1s, you're going to start to see this add up quickly. Your queuing delay. When people talk about utilization, if you're using 500 megs per second on a gigi interface, people say that it's 50% utilized. But in reality, an interface is either 100% utilized or it's 0% utilized. Either you're transmitting or you're not transmitting. So what you're actually talking about is utilization over time. You're saying 500 megabits per second. You're taking a 1 second average and you're saying that 50% of the time over that 1 second I'm transmitting. But in reality, when packets come in, a lot of the times the interface is transmitting. So when the interface is transmitting, you can't send the next packet, so it has to be queued. So even if an interface isn't completely full, you're going to see queuing. You're just going to see very small queuing. But as an interface starts to reach saturation, what you see is the amount of time the packet is queued in the router goes up exponentially. And then when an interface is very full, you may see that the packet spends hundreds or thousands of milliseconds sitting in a router buffer before it can get transmitted. But it still gets through. Even if the interface is 95% full, it still gets through, but it's going to spend a lot of time sitting in the router waiting, and you're going to see that latency in your traceroute. The buffers depend on the router type. Historically, the line of logic has always been that a core router needs 200 milliseconds of buffering. So when you're talking about a GSR, CRS1, a big Juniper, that's the kind of value that you'll tend to see. A lot of the Ethernet devices that people are using, like Cisco 6500, 7600s, or Foundries, whatever the case, have much smaller buffers. So you may not actually, an interface may be congested, and you may not actually see that on a device with a very small buffer because it can only hold, 0.5 milliseconds worth. You just get drop packets, but you don't see the huge times. Whereas if the router has a big buffer, you might see the 3,000 millisecond time. And then obviously the other cause is propagation delay. And this is the big one that you can't really, what I always tell people is when they complain is take it up with God. Light only goes so fast. So I did the math here for figuring out how fast light goes through fiber. And fiber is not the most efficient medium for transmitting light, but you get about 0.67 C through it, which is around 200,000 kilometers a second. So you can divide that out by millisecond and see that one way on the fiber is about 200 kilometers or about 125 miles per millisecond. And then you cut that value in half or multiply whichever way you want to do the math to take into account round trip. And you can see that for every 62.5 miles of fiber, you're going to see about 1 millisecond added to your trace route. So you can actually do the math on that and say, well, if I have to go around the world, the equator, it's going to be 400 milliseconds. That's speed of light. That's something you can't change. So, well, you don't need to do the round trip, but that's coming. Okay, so you have to identify if the latency affecting you is normal or not. A lot of times people are going to open tickets for problems on routers. Oh my God, my latency just went up 67 milliseconds. This is horrible. Well, it's actually not horrible because you're going 4,200 miles. You're going from New York to London. And this is why you need to know where your router is located because now you identify that this is actually a long-distance fiber route. Another example where you see two routers in DC and you cross a network boundary and all of a sudden it goes up 200 milliseconds, that's probably not propagation delay. That's probably congested interface or something else. The other thing that comes into play with Traceroute is prioritization rate limiting. So, the architecture of a modern router is very different depending on whether you're forwarding packets or sending the packets to the router. So, assuming that you're forwarding packets through the router, that's called the data plane. And in many cases, there's actually multiple paths within the data plane. There's the fast path, which is optimized to be as efficient as possible. And in modern routers, what you're going to see here is this is entirely hardware-based. It's for forwarding ordinary packets to ordinary places, and you're going to get millions or hundreds of millions of packets per second. Then there's also going to be a slow path, which is how you handle exception packets, things that need CPU to handle. And this is going to be many orders of magnitude less capacity. Examples are things like IP options or things where you have to generate an ICMP. And then separately from packets being forwarded through the router is packets being forwarded to the router, which is the control plane. Examples of that are, your BGP or IGP packets, SNMP to the router. When someone's sitting there on the router on the CLI typing show IP BGP and it's doing a big calculation, that's consuming CPU. Anytime you ping the router, anytime you send anything to an IP that's configured on the router itself. And these CPUs tend to be very underpowered. You will see 300 to 600 gigabit per second routers with 600 megahertz CPUs, and generating ICMP is not a priority for them. The other problem that tends to happen is a lot of platforms share the slow path processing and the control plane share the same resources. So when someone's forwarding packets to the router, even if it's not going to the router itself, even if it's going through the router, but it's a type of packet that requires processing, it's going to consume the same CPU. Or if someone is logged into the router on the CLI and is doing show IP BGP regex and the router's doing a lot of calculations, it's going to impact the slow path forwarding. So the problem is a lot of these routers don't tend to have the best schedulers. They're not prioritizing handling the ICMP packets in real time. So when someone is using the CLI or when BGP is churning or whatever the case may be, you're going to see spikes in your latency. And the most infamous cause of that on all Cisco iOS devices is BGP scanner, which is a process that runs every 60 seconds that walks the BGP table. And every time it does, your traceroute latency spikes through the roof, and people see that. And the other issue is that most routers rate limit their ICMP generation in some way. And the bigger problem is that they do it with hard-coded values which are not published. So for example, Juniper has a hard-coded limit of 50 packets per second per interface, and depending on the type of FPC or depending on the type of router, and they've upped the limit in new codes, but it's still a hard-coded limit that you don't know and don't have any ability to configure. There's a limit to the number of ICMPs that can be generated. So if you have 20 people individually running Traceroute through your network and they all hit the same router in that same second, you might be dropping some ICMPs, and people might be seeing that as a false limit. And I have some other vendors, but the point being, most vendors have some kind of arbitrary hard-coded rate limit.
Cisco's kind of all over the spectrum there because of the different ways that they require their hardware.
Yeah, Cisco has a lot of values. I didn't get any good concrete numbers to throw into the presentation, so I can't say for sure, but it definitely differs depending on platform and code and whatever. So you, as the person looking at a traceroute, need to be able to spot the fake latency and figure out if it's actually a problem or not. So the most important rule is if you don't see the latency continue forward, it's not an actual problem. So here's an example of a latency spike. I ran Traceroute 3 times, and there you go, the third time there's a latency spike. But that's not actually a problem because, as you can see, the third hop, it continues on normally. So that's what I tell a lot of clients and customers that look at this and say, well, somewhere in the middle there's a big spike. And what you can say is, by definition, if the spike does not continue, it's not an actual problem. It's only something happening on that one router. Because if it was a problem with forwarding, you would see that in all future packets. The other big problem with Traceroute, in fact the biggest problem, is asymmetric paths. Remember, because you're looking at latency that is calculated based on the time that it takes for your probe to go out plus the time that it takes for the ICMP message to come back, you have no visibility into the return path. So you have no idea where the problem is, where the potential problem is. That's a big problem for Traceroute. And the asymmetric paths can even change somewhere in the middle. So you can have a Traceroute that's clean at the beginning and clean at the end and really high in the middle, and you might think that it's a prioritization problem, and in fact, no, it's actually a forwarding problem, but it's a problem that only affects packets coming from that one router just because of the asymmetric paths, and you really have no visibility into that. The reason that you care about asymmetric paths and network boundaries is because that, like I said, that's where the administrative policies start to change. So here's an example where you might look at this path and say, oh my God, global crossing, Sprint, congested, there's a problem, call one of them. And it turns out that isn't actually the problem at all. What's happening is as soon as you cross the administrative boundary, now Sprint is taking a different path back to whatever your source is. And that might happen to go over something that's congested, or that might happen to go over something that's just a longer path, but is otherwise fine. And you really have no visibility into that. You would have to have the destination do a traceroute back to you. You, as the person launching the traceroute, has no visibility into the return path.
So essentially what you're saying there is that here's your problem to see because you don't want to build up some return path.
Right, and there may not be a problem in DC. There may not be a problem on the return path at all. It may just be a longer path that might actually not be congested. So, as the person working the traceroute, your best option, well, your best option is to get the reverse traceroute from the other side. And the problem is a lot of times you can't do that, or for some other reason people can't. You have a question? Definitely. There's tools being developed and things like that where you can get the return path, and that's actually a great thing. So I'll definitely be attending that. But assuming that you're stuck with ordinary traceroute and you're trying to figure out the reverse path or figure out if it is an asymmetric problem or not, the most powerful tool you have at your disposal is setting your source address. So, for example, the previous example, say you're a network that's multi-home to global crossing level 3. When you send the packets out and it's still within the global crossing network, global crossing sends it back to you. As soon as you cross an administrative boundary, now Sprint is sending it back via level 3. And say, for example, there's a problem between Sprint and level 3. How can you figure out if that's an asymmetric path problem or not? And the most powerful tool you have at your disposal is to set your traceroute, set the source address of your traceroute from your global crossing IP. And the reason that that's effective is in the case of a transit provider-customer relationship, almost always the transit provider is giving you the /30. That's coming out of their IP space, which is routed via their policy. So you're pretty much guaranteed that if you set your traceroute source to your global crossing /30, it's going to come back via global crossing. So if you compare that to something that might be routed via both paths, like a regular IP in your network, you can potentially see if there's a problem on the reverse path or not. But remember that asymmetric paths don't have to be network boundary related. It can just be an issue of closest exit. So in this example, your first traceroute probe, you're sending it across a network boundary in Washington, D.C. It goes out Chicago. It crosses a network boundary in Chicago. It comes back to you. Your second probe, it now crosses a network boundary in San Jose. So that can happen anytime just based on multiple exits and hot potato routing. But what if you're troubleshooting a peer, something that's come out of your 30 or a customer IP space or whatever the case may be? And it turns out there's actually some benefits that you can still see from setting source addresses based on that. The reason is a lot of networks will redistribute their directly connected interfaces into their IGP. So that /30, even though it's your IP space, may now be routed by that network by the network that you're directly connected to completely differently than other IPs. So in the previous example, where the packet might be coming back via San Jose now on the second hop, if you set your traceroute source to the /30, it might now be coming back entirely symmetrically, or at least more symmetrically, on their network. So you're always guaranteed that if they are carrying that 30 in their IGP, that it's going to come back to you via that same interface. So just the act of looking at the different paths, you can determine whether it's an asymmetric issue or not just by comparing the two, versus sourcing the tracer route from a loopback or from a host or something else in your IP space. And the more viewpoints you have, the more you can figure out what the problem is. One thing that people forget a lot of times is there's default source address selection on a router. On a Cisco, for example, the default is to source the traceroute from the egress interface IP. So if you're on that router with your transit to global crossing and the packet goes out global crossing, it's automatically going to set the source address via whatever that /30 to global crossing is. Other platforms give you the option, and a lot of people configure this option, to default to sending out from the loopback. So for example, on a Juniper platform, you might be sourcing from something that is not that situation. And sometimes you want to, you have a router with multiple connections, and even if the egress is going out one direction, you probably might want to set the source address to something completely differently to control the return path. Another issue with Traceroute is the handling of multiple paths and load balancing. Because Traceroute by default uses, or the classic implementation I should say, uses UDP or TCP or something that has layer 4 headers, as the packets go across the network, there's the opportunity for them to be hashed over multiple paths. So here's an example of Telia running parallel links through 3 different hops, and it's completely harmless, but it might confuse some people to see that one of their probes goes over one router and the other probe goes over another router. And if you're troubleshooting a problem, maybe the problem is only on one of these paths. So here's a slightly more complex example of that. Here is NTT, or Vario, load balancing between Ashburn and Seattle, where one path goes Ashburn, New York, Seattle, and another path goes Ashburn, Chicago, Seattle. And these have different latency times, different times in the middle. If you don't know to expect that, you might be confused, and you might think my packet goes from Ashburn to New York to Chicago to Seattle twice. What? You don't know? There's a lot of people out there that don't know that. So the big problem, and I couldn't find a good example of this because it's such a nasty problem that it scares and confuses people, is when you're load balancing over unequal length paths. And the problem there, in this example, on hop 2, there's a second router that's being inserted into this parallel path that I call X. And so going forward, what you see now is the parallel paths are actually not parallel anymore. One is lagging behind the other. And so when you're looking at your traceroute, you can see the packet. You might think it's going forward to a city, it's coming back, it's going forward to another city, it's coming back again. It's extremely confusing. It makes the traceroute very difficult to read, and it freaks end users out like nothing. So when in doubt, when you think that there's a problem with multiple paths, you can configure your traceroute client to only send a single probe. The advantage there is you're only looking at one path, so now it's very simple to interpret. The disadvantage is that might not actually be the path that your traffic's being forwarded over. And it's very common to see a problem with one link on the parallel path. A lot of networks these days are running 16 by 10 gig where one link starts taking errors, and it might appear to you to be completely arbitrary. All of your trace routes might be clean and normal, but the whatever application you're running might just be going over that one bad link. So you lose visibility into all those paths. And then the other big problem, or confusing problem, is the interaction of MPLS with Traceroute. So obviously a lot of ISPs run big MPLS-based cores. And the one really obvious thing is that with MPLS, you don't actually have to show the router hops in the middle. You can turn off TTL decrement, and to Traceroute, it will look as though the packet came in the one side of the LSP, came out the other side as all one hop. But even more than that, a lot of networks don't carry IP tables in the middle. They have a dedicated router that just does label switching, doesn't have an IP. So if it is doing TTL decrementing, how does the ICMP get back to you? How does that router return it to you? And if it doesn't have an IP table, the answer is it may not have a good way to do that. So there's an option that some networks configure called ICMP tunneling. And what happens is if the packet is in the middle of an LSP when the TTL expires and the router is now generating an ICMP coming back to you, it puts it back into the same LSP that it was already on. So what happens? You no longer have the same model where the packet now comes back to you at each individual hop. What happens is the packet travels all the way to the end of the LSP before coming back, and so it makes every hop along the path look like the same latency. So here's an example of this happening in AT&T, where you might be confused and think Palo Alto to San Francisco is 74 milliseconds. There's a problem. But you'll notice that it's actually 74 milliseconds the entire way through. That's because there's an LSP from San Francisco to New York, and the return packets, all the ICMP is actually going to New York and coming back to you, even if it's being generated in San Francisco. And that is the conclusion of my talk. A little early, probably. So hopefully there's some questions.
Thanks a lot for putting this together, Ras. I think, to me, this tool has been around, since forever, and it remains sort of the stone knives sort of mentality to dealing with these problems. Clearly, you don't expect your grandmother and end users all over the globe to type in these archaic commands and try and interpret this sort of stuff. So I guess my question is kind of a general one. What network instrumentation do we need to have in place so that proper information gets to the network service providers to be able to deal with real issues on the end user's behalf?
Well, the problem there is that a lot of people actually are running these commands either because, it's the type of person that reads DSL reports and wants to tweak their router to download a little faster, or it's because of some tool like a visual traceroute or some program that people now type in the site of the thing they're having a problem with, or someone's complaining about their gaming, and so they type in the server and they see this traceroute pop up, and now they a lot of these tools even put the who is there, who to contact, who to complain to, and the problem is a lot of these people that are running the tools don't have the experience to actually troubleshoot a problem. What you really need to do, and there's only so much you can do as far as educating people how to read a traceroute. But the point that I want to make is that it's not as simple as just looking at the traceroute. It's like reading an EKG. You're not just looking for the bumps. You have to be experienced. You have to know what the pattern is. You have to really understand why things could be happening this way. But one of the things that you can do is provide access to see the return path, either through everyone having a looking glass in their network where you can run a traceroute from different points in the network, or protocols, extensions that are being written where you could request the remote side to send back something to you. One of the things that I didn't mention in here is there's actually an option called record route in IP where you can what will happen is each router along the hop will actually process the packet and it will insert its name into the packet. So you might send a ping out to someone with a record route option, and you might get the asymmetric path or the return path, and you might be able to see that. The problem is because that is processed as an IP option, it's CPU demanding on the router, and so most people have it turned off at this point, especially on trace routes. So there's a few networks where you might be able to use that, but for the most part, it's not a reliable tool.
Just one last point. It seems like we ought to have something physically within the network that does the appropriate monitoring and digesting and presenting, maybe not to the user, but rather directly to the ISP. So rather than dealing with end users, asking them to mail you the traceroute, the data that they're using to say that there's a problem in your network, you ought to be proactively taking a look at it and maybe the network ought to have a direct feed that obviates the need for Traceroute. That was just a thought.
Right, definitely. And the way that you would want to implement that is, instead of doing it as an IP option, to do it as a protocol where you can request a remote traceroute. And if that was something that everyone could enable on their routers, where you could have anyone request that router run and send them back the results of a remote traceroute, that would be very helpful. Danny?
Hey, Richard. Thanks again for throwing this together. I've been answering this question over the years many, many times. So I think from now on, I'm just send people to your PDF and say, read this first, and then call me if you have any questions. I just last week I was looking for something, and there were all sorts of sites out there, and none of them were actually really comprehensive. That's good. I want to ask you about, I'm seeing more and more MTR tool use, and I'm finding myself explaining MTR a little bit differently than output of Traceroute. What do you think about MTR, and how would you explain that as different than Traceroute?
I have mixed feelings on MTR, just because MTR is the source of a lot of false complaints. And really, that's not a problem with the tool itself as so much as it is a problem with the users. MTR is basically just a curses-based traceroute that runs the traceroute over and over and over. So instead of sending 3 probes, it just continuously updates, starts back from the top, runs the trace again, runs the trace again. So you may get hundreds or thousands of probes. There's a problem in that is increasing the load on the routers, which is causing a lot of routers to start bumping into these hard-coded default limits. But as a tool itself, it's fine. The issue is just, if you're still not able to interpret it, now if you do run 1,000 probes to every router in the middle, odds are very strong that one of those routers in the middle is going to drop a packet, and that's just going to confuse end users.
A couple of things. Also, you didn't mention it because it's not an issue today, but if we all remember the time where AT&T was running the Avicii TBRs, and Level 3 was running code on their Force 10s, where sometimes you would either see no response or 1,000 to 2,000 millisecond response. I don't know if you've been seeing that at all on modern internet today.
I haven't seen that kind of problem caused by prioritization, but I've seen, if I run a traceroute 5 times across my network, odds are good that one or more of the routers is going to have a big unexplained latency spike, or maybe even a drop, and it's not actual loss, it's just a problem with running traceroute. So maybe vendors need to put a little more time and detail into improving their traceroute response, either improving the scheduler or having some kind of dedicated processor, whatever the case may be, to make that result appear more clean. But I typically see something like 100, 200 milliseconds caused by, if I'm logged into a router doing a big complex show route, it's going to slow it down, and that might cause problems with the traceroute.
I like that idea, either like a Juniper Traceroute pick or a Cisco Traceroute services module, or you have Force 10 put a 4th CPU on their next rev just for responding to. And the last question I have is, how do you explain when your end customers are showing you traceroutes where, so there's time-based speed of light, but a lot of cable modem and DSL services, oftentimes the first hop might have 15 to 25 milliseconds, and I'm having a hard time explaining that to end users.
You definitely see that, especially with cable modems, and the problem there being, DOCSIS is a TDMA protocol. By the way that it works, there's going to be a lot of variable delay in there. Some of that is actually caused by serialization delay. If you've got a DSL and it has 1.5 megs down, but it only has 256K up, that is actually slow enough that you're going to see serialization delay. And so people will see an extra 10 milliseconds, 15 milliseconds on their traceroute and be concerned. And it is a legitimate concern, because when you're sending a 1,500 byte packet, that's a big delay. So a lot of the very hard caps that are imposed on upstreams, is definitely going to start to contribute to that. But a lot of the problems that we see, we have customers complain, oh my God, it's horrible latency across your network. Yeah, it's horrible latency starting at your first hop. And a lot of that's just human factors. You just have to explain to people. Go talk to your cable provider. And of course, the cable provider won't talk back, so. Yes. No, I've legitimately seen people send in trace routes where it's 3,000 milliseconds on their first hop, and it turns out the computer in the next room is running BitTorrent, and they left it on, and they're filing a complaint with me. So, yeah.
That was interesting. So you were talking about the problems with multipath. There was a research project a couple years ago that came out with a variant called Paris Traceroute that most academic groups are using for their traceroute now. Like, that's what I use. Mm-hmm. And it's just meant to deal with multipath. And so I was just curious if anyone's using that, if there's any penetration. There's sort of two options. One is just to keep the port consistent so you get a consistent path. And then the other option is to vary the port systematically so that you can expose all the multipaths and sort of see, especially when you have unequal length ones, what's going on. Do you ever use that? Do you know anyone who does?
So I read a paper on Paris Traceroute, and I remember when I read it seeing some problem that I thought would be an issue, and so I haven't actually used it, but I did remember seeing it. I'm not aware of anyone that uses it, but that's one of the things that I've done myself when I implement my own tracer routes, is the systematic approach of run a complete tracer route with a single port, then run a complete tracer route with an incremental port, and try to explore the different paths that are out there. Probably one of the more interesting things that I've seen, and this is a problem with networks that now have to run very large link lag groups to handle their network. You've got big networks like Level 3 running 16 by 10 gig parallel paths across their network, and that's not visible to IP. So there's been some work in the IETF for a protocol that would cause the packet. So the approach the IETF was taking was to cause the packet to flood like a tree. I'm not convinced that that's the best solution. Several other people. Yes, many people are not convinced that that's the best approach. Maybe the best approach is some kind of ability to control the paths, or some kind of ICMP query to look at what are the available paths, something like that, so that you could actually have an IP layer tool that now has visibility into all these parallel paths, and you could control, you could say, take this path, take the next path, take the next path, and systematically test. Yeah, I don't recall offhand, but Guy.
Hey, Richard. Guy. Yeah, it was a good presentation. I would say it was good that you brought up the record route. I was going to bring that up, as well as the MTR. And then the other thing also is, you can actually specify with Traceroute to go through, some arbitrary IP along the way, so you can sort of route around where you're seeing some congestion if you have a good enough topology of the network. So
yeah, the problem is that's source routing, and that's IP option based. So most networks turn that off. There's a handful that leave it enabled on their edge for troubleshooting, but these days, honestly, most networks do turn it off. So that's just.
Yeah. Well, I mean, for at least the ones that don't, I mean, I think it'd be useful to add and maybe even like TCP traceroute, just to explicitly mention that, just so people looking at this in the future can say, oh, well, here's some of the actual tools to use. I don't know, suggestion.
Yeah. One of the things to keep in mind with TCP traceroute, there's actually a lot of networks that do policy-based routing where your traceroute might go out over a nice expensive internet path, and your port 80 TCP might actually go out over Cogent. You'd be surprised the number of people that are doing that, and so TCP traceroute can help uncover some of the shenanigans that go on.
It's Marco Extrol, and basically on the same subject, and your comment on MTR, just keep on repeating Traceroute, and I think the main difference is that MTR actually spits out ICMP echo instead of UDP. And I think that might influence your Traceroute results or your MTR feedback.
So actually, I wasn't clear on the behavior of MTR because I used to think that what it was doing was, after it discovered the network with Traceroute, it was sending ICMP. And somebody actually told me that it wasn't doing that. It was actually running multiple trace routes.
I also was doubting, and I can show you the Traceroute on the TCP dump on my laptop. I just did one.
Yeah.
The current Debian host I was testing runs ICMP ping. when I
Okay.
started.
Well, if it is ping, and I swear that must have changed in versions because I did, had someone point that out to me, and I said, no, it's ping, and they found some documentation that proved that it wasn't. But if it is running, if it's running the first trace route to discover the topology, and it's running the second one as ping, which I don't think that it's doing because I've seen it come back and fill in, after the second, third, fourth path. I've seen it come back and fill in ECMP. So it is definitely whatever version I'm running multiple trace routes. But if you are looking at a tool that uses Traceroute to find the topology and then pings the router, you're going to get very different results on that because a lot of networks are running rate limits on ICMP on the routers. So that's something to keep in mind, that's no longer a forwarding path issue, that's a control plane issue. So for example, on Junipers and probably some other platforms, there's actually a separate processor for handling ICMP generation of data plane packets versus the routing engine control plane. So you might see different results based on that. Any other questions? You set the evil bit.
Hi. We use looking glasses a lot too to find the reverse path, but regrettably not everybody is running them. So if you can allow them on your network, please get them up and make sure Google finds them or put them somewhere like bgp4.as so other people can find them and use them. Or if you know any other sites that summarize looking glasses.
There's a couple sites that summarize looking glasses, and every time I look at them, they're out of date. Traceroute.org is constantly out of date. That's the problem that I see. Most of the time, Google finds them, or they don't exist. And there's several large networks like UUNet, NTT, various people that don't have looking glasses that are real pains to troubleshoot. So anyone that wants to give those guys a kick, please. Anything else? Yes, I'll forward it to you.
I just want to add, we have time to kill here. An interesting place where I'm seeing more trace routes coming up is a lot of monitoring services have started to add that to their alerts. So where previously we're seeing the Keynote alert site Gomez's would just tell you problem. More and more when they're doing, for example, HTTP-based monitoring, when an alarm comes in addition to telling you they have an alarm, they email a trace route, that snapshot in time, a TCP-based trace route, which is actually kind of useful. And some of the sites, alert site, for example, because that's what I spend most of my time staring at because it's cheap and people like saving money. They to give you the IP address they issue the traceroute from, and then they show you the traceroute, which makes it really easy to slam a traceroute back to them. So
I really wish more tools did that. If the tool just said the source address when it ran the traceroute every time, and the timestamp, that would be very, very helpful.
And another interesting note is that some of the TCP trace routes don't actually make a real TCP packet. They just make an IP packet with the protocol set. They also just ignore the fact that you specify a port. So, you do -P80 and it's still just an IP packet, which makes things fun.
Definitely. I don't have much experience with the TCP traceroute tools, but I could believe that that's a problem. No, I don't. Well, otherwise, I think that's it.